When we're discussing the chain rule here in section 3.7, I need to make sure that you get this concept down really well because it's going to follow you throughout every calculus class and every other math class hereafter, even after the calculus sequence. Extremely important concept. So to compare and contrast what we have been doing with what we will be doing, we've already taken derivatives of power functions, exponential functions, and trig functions. But the power functions we've dealt with have looked something like this, where we have 7 over just the root of x. The only thing inside the square root is the x term. Well, we quickly rewrote that as 7x to the negative 1/2 power to make it more efficient to be able to take the derivative. We just say, well, that's just the function to the negative 1/2 power, so we use the power rule. The negative 1/2 comes down, multiplies the 7. I get negative 7 over 2, x to the negative 3 over 2 power. And then, of course, we can simplify that and say that x to the negative 3 over 2 means that that x term belongs inside of a square root to the third power in the denominator. And so we'd have negative 7 over 2 on the root of x cubed. Now, we've also taken the derivative of constants and exponential functions. You know that the derivative of any constant is 0. The derivative of any exponential function is that exponential function, including its constant coefficient. So the derivative here of g of x would be negative 10 e to the x. But then again, that's it. There's nothing else to it. So these derivatives, pretty easy, pretty quick. If you have a tangent function, you know that the derivative of tangent is secant squared, so the derivative of 3 tangent x is simply 3 secant squared x. Okay, but what if we make these functions more interesting? And by more interesting, I mean, well, what if it's a function inside of a function? You've dealt with the composite functions before in your algebra classes. Now we're going to see them from the calculus standpoint. So instead of the power function just simply being 7 over the root of x, what if it's 7 over a function of x? In this case, 8x plus 5. And you'll see I have it rewritten over here. This is the same thing we did up here. You called the x to the negative 1/2. Now I would have to call it the group 8x plus 5 to the negative 1/2. We haven't seen how to take the derivative of anything like this yet. Similarly, instead of just having an exponent of x in my exponential function, what if it had an exponent of 6x squared plus 3? Or what if my tangent function had a function on the inside of it instead of simply an x? Well, what if it had 10x to the 4th on the inside? So now we've got to think about how we're going to do derivatives of these types of functions. And the way that we're going to do that, the answer is the chain rule. It's going to allow you to take the derivatives of functions which are used in composition with other functions. So anytime you have a function inside of another function. So I want to show you how the chain rule works. The main skill that you're going to need to hear is to be able to recognize the composition and being able to recognize the inner and outer function. If you can't recognize that in the problems, then we're not going to be able to take the derivative successfully. Okay, so the chain rule in its basic premise is just that if you have a function that's a composition of other functions, so in other words, if g of x is a function of x inside of f of x, then we should be able to take the derivative and say that h prime of x is just going to be whatever the derivative of the outside function is, evaluated at the interior function, then times the derivative of the interior function. Okay, so now what if I look at a function like this? This will give us our first example. I'm trying to take the derivative of y is equal to x squared plus 2x minus 5 to the 15th power. So I said the outer function is that 15th power, and what's on the inside of that is the quadratic equation there. So I can say, okay, derivative of the outside, it's a power rule. We bring the 15 down in front times the group left alone. That's where this in here comes into play. You take the derivative of the outside, leave the inside alone, then times the derivative of the inside. Well, that's exactly what I'm doing here. Derivative of the outside, 15 times the group left alone to the 14th power. Then I needed to say times the derivative of the inside. Now, of course, we know that the derivative of the inside, derivative of any polynomial, you can just use the power rule for each individual term. Derivative of x squared is 2x, derivative of 2x is 2. So I get this as my derivative, and then I can simplify that. I can factor a 2 out of this group. When I do, that's going to make the constant coefficient out in front 30. And then I'll have times the group x plus 1 times this group to the 14th power. Pretty nice. Now, well, what if we had a problem where you have a root in the denominator? Same thing as what I did back on the previous page. You're going to need to simplify that and say, well, I can call that root as the negative 1/4 power in the numerator. So I would rather think of this as 3 times the group 6x plus 5 to the negative 1/4. Then I can see, okay, I have a function inside of a function. Take the derivative of the outside first. The outside is the power. Power rule tells you to bring that negative 1/4 down in front, multiply it by the 3. That's where I got the negative 3/4 there. Then you say times the group left alone to the one lower power. Well, negative 1/4 minus 1 is the negative 5/4 power. Then we say times the derivative of the inside. That's where that 6 comes from. Now I need to simplify. Well, that's 6 times the negative 3 over 4. That would give me negative 18 over 4. And I know negative 18 over 4 reduces down to negative 9 over 2. Notice that's where that comes from. Negative 9 over 2. Then I needed to understand, because of this negative exponent, that tells me that this group belongs in the denominator. It's going to be the 4th root of 6x plus 5 to the 5th power in the denominator. And then I would have my final gorgeous answer there. Now, what if we have the chain rule with exponential functions? Well, when I have exponential functions here, basic rule here, e raised to the f of x power. If I'm trying to take the derivative of that, derivative of any exponential function is that exponential function. And now we just need to remember times whatever the derivative of the exponent is. Now I put a general exponential function derivative here. If we have the derivative of e to the f of x, this is all we ever need. But what if it's some other base, like 2, like 5, like 10, any other number other than e? Then you would say the derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of whatever its base is. Up here it's not needed, because if you multiply by the natural log of e, you're just multiplying by 1. So up here you don't need it, but in any other base you would have to multiply by the natural log of the base. Now, if I take the derivative of a function like e to the negative 8x plus 12 power, I know the derivative of any exponential, it is that exponential function times the derivative of the exponent. That's where the negative 8 comes from there. Then you can say, well, that negative 8 can and should be brought out in front of the exponential function, and then I have my final answer. Pretty quick problem. Same thing over here, though. You say, well, what if you have a constant and an exponential function? We always know the derivative of any constant by itself is 0. Now here, that constant is multiplying an exponential function, so it's going to get carried along in the answer. And I can say, okay, the derivative of negative 10 e to the 6x squared plus 3 is negative 10 e to the 6x squared plus 3 times the derivative of its exponent. The derivative of 6x squared is where the 12x comes from. And then notice what I did from this step to the next. I just said 12x times negative 10 is a negative 120x. To get my final answer there, negative 120x e to the 6x squared plus 3 power. Now, one thing that I want to make sure that you understand here, whenever we're talking about exponential functions, I had an exponential function here and here. Whenever you're dealing with those exponential functions, the argument in the exponent will never change when you're taking the derivative. So yes, you're going to multiply by the derivative of the exponent, but that's going to multiply the base of the exponential function, certainly not going to change the exponent. Here's another example here. If I have 17e to the secant of x, and I'm asking you to take the derivative, you're supposed to be thinking, well, the derivative of any exponential function is that exponential function, 17e to the secant x, times the derivative of the exponent, well, times the derivative of the secant of x. Now I know that the derivative of secant is secant x tangent x, and so now all I did is I multiplied all these three together, and to try to emphasize that the exponent is not changing. When you're multiplying by the derivative of the exponent, you're not multiplying by that in the exponent. To try to make sure I showed that, I brought the secant and the tangent out in front with a 17, and then showed the exponential function is still only raised to that secant of x power. The exponent of an exponential function will never change through derivatives. Now, speaking of something else that won't change, the angle of a trigonometric function will never change through differentiation. So that's what I'm trying to show on this page. I have our chain rule derivatives here for all of our 6 basic trig functions. And so we can say here for this first one, I'm trying to take the derivative with respect to x of the sine of f of x. Well, you know derivative of sine is cosine. You keep the angle, and then you multiply by whatever the derivative of that angle is. Derivative of tangent is secant squared. Keep the angle f of x times f prime of x. Derivative of secant is secant tangent, and please remember that angle goes with each portion of that answer, so it's the secant f of x, the tangent of f of x, but then the chain rule says you need to multiply by the derivative of whatever the angle is, well, f prime of x. Same thing over here with cosine, its derivative is negative sine of that angle f of x. Again, you multiply by the derivative of that angle. Derivative of cotangent is negative cosecant of that angle f of x times the derivative of that angle. And derivative of cosecant is negative cosecant cotangent. The angle f of x goes with each of those portions. And then again, just as always, you multiply by the derivative of the angle after you've taken the derivative of the trig function. To show you some examples of these, and again, please notice I'm trying to make sure I emphasize this because a lot of students mess up on this. Whenever you're taking the derivative of a trig function, the angle or the argument inside of the trig function will never change. So if I say take the derivative of the tangent of 5x cubed, well, derivative of tangent is secant squared. I'd keep the angle 5x cubed. Then I'd multiply by the derivative of that angle. Well, derivative of 5x cubed is 15x to the second. I could bring that 15x to the second out in front of my secant squared of 5x cubed and be done with that problem. So, you're probably thinking, well, that's pretty short. A lot of these problems are pretty short, especially if it's just the 2-layer chain rules like we're looking at now. My next one, again, it's a function inside of a function. So you're asked to take the derivative of the cosine of 10 minus e to the x. And you say, well, the derivative of cosine is negative sine. You keep the angle 10 minus e to the negative x, and then where this comes from is you needed to multiply by the derivative of that angle. Well, the derivative of 10 is 0, but the derivative of negative e to the x is negative e to the x. And again, remember, that doesn't change the angle. It's multiplying the sine function out in front. So I had a negative times a negative. That's how that e to the x became positive. And then I had my sine of the angle, 10 minus e to the x. The next one down here, anytime you have trig functions written to powers, typically the way that we write powers is right after the trig function. But please remember, it means the same thing as this. So if I ask you to take the derivative of secant cubed x, you need to understand, okay, that's nothing more than the secant of x all raised to the third power. Then I can say, well, the derivative, I know that the inside function is the secant of x, the outside function is x cubed. So the outside function is a power function. I have to use the power rule. When I take the derivative, first step is 3 is going to come down in front of the group, times the group secant of x to the second power. That's where all of that came from. And then you say times the derivative of the inside. Well, the derivative of secant is secant x tangent x. So now I get my answer. Let's just simplify it. You have a secant squared x here times a secant x here. For the final answer, I'd prefer you to put it back towards the original format. So that's going to be secant cubed x. And then I also had a tangent x along with a 3 in that answer. Pretty nice problem. Now, let's work towards more beautiful problems. The more beautiful problems have more compositions within the problem. So I'm saying the chain rule may be needed more than once, and you should never ever be left wondering in a problem whether or not you've used the chain rule enough. It's pretty easy to see if you'll look at the original problem. And here's what I mean. You need to see that you have the function 2x inside of the cosecant function, which is then inside of the exponential function. So you have a function inside of a function inside of a function. That's why I put here you need to recognize the 3 layers of composition, because each part of your derivative is going to have to address one of those layers. So first layer, well, everything's inside of the exponential function, so I need to say derivative of any exponential function is that exponential function. Done. That's the first layer. This is the derivative of 3e to the negative 2 cosecant of 2x. Derivative of any exponential function is that exponential function. Now I have to say times the derivative of what was on the inside of it. Well, what's on the inside of it is this negative 2 cosecant of 2x. Here's where I need to remember that the derivative of cosecant is negative cosecant cotangent. So the derivative of negative 2 cosecant is going to be positive 2 cosecant cotangent. I keep that angle with each one of them. That's the second layer. And then you can say, yeah, but that angle was not just x. So I had to address that in the third layer of my derivative. So the derivative of this exponential function was derivative of the outside, the exponential function, times the derivative of the trig function within it, now times the derivative of the angle inside of that trig function, derivative of 2x being 2. Now you just need to clean this answer up. I had a 2 times a 2 times a 3 for a factor of 12. My exponential function e to the negative 2 cosecant 2x, remember, the exponent of an exponential function will never change. But now that exponential function is being multiplied by cosecant 2x cotangent of 2x. I could have brought those two terms out in front too. Doesn't really matter the order you write your answer in. Order of multiplication is irrelevant, just as long as you make sure you're not showing that those terms go up in the exponent with that. Up next, again, I'm doing a 3-layer derivative problem. You have the function 4x squared plus 1 inside of the square root function, the square root of x, which then is the angle inside of the tangent function. So your derivative is going to have to address all 3 layers of that composition. The first layer, derivative of tangent, secant squared. I keep the angle. Then I say, well, times the derivative of that angle. But then when I do that, I can say, well, the angle is a group to the 1/2 power. So power rule is what I have to do first. The 1/2 came down in front, times the group left alone to the negative 1/2 power. And then you can say, okay, you're not done because you've taken the derivative of the square root here using the power rule. Now you need to multiply by the derivative of what was inside of that. And what's inside of that is 4x squared plus 1. Its derivative is 8x. Please notice, first part, second part, third part. Your derivative has to address all 3 parts of the composition of the original problem, and mine does. So now it's just a matter of simplifying. You had 8 times 1/2, that gave me a factor of 4 in the numerator, along with a factor of x in the numerator. And I knew I would have a secant squared of that angle in the numerator. My denominator is just going to become this factor of the square root of 4x squared plus 1. And so then I can say, well, that's a nice, simplified, good-looking final answer there. What if we have the chain rule inside of a product rule problem? I know what you're thinking. That makes it more cool. It really does. So here, whenever you're doing the product rule, I'm doing derivative of the first one. I had the group 3x minus 7 to the fourth. So I said, well, the outside is the power. 4 comes down in front using the power rule times the group to the third. Times the derivative of what's on the inside. That's where the 3 comes from. Times the second, plus the first, 3x minus 7 to the fourth, now times the derivative of the second. Derivative of any exponential function is that exponential function times the derivative of its exponent. So now I come down to the next step, and I'm supposed to factor in this step. So I looked at my two terms, and I'm trying to pull out my greatest common factor. The first group has a constant factor of 4. The second group has a constant factor of 20, which nicely for us, 20 does have a factor of 4. So I'm going to factor a 4 out of both groups. Both groups also have the 3x minus 7. I factor it out to the third power. And both groups also have the e to the 20x. It gets factored out. Whenever you factor out the greatest common factor, your first group, the only term remaining is this 3. Every other term canceled. I just have a 3 left there. Now I say plus, well, in the second group, you're going to have one factor of 3x minus 7 to the fourth left over. Now it's to the first power. Your e to the 20x canceled out, but not all of your factor of 20 canceled out. You factored out a factor of 4. 20 divided by 4 leaves you with a factor of 5 there. Now the only thing I've done from this step to this step is I simplified that last factor. You don't want any multiplication if those terms are not factors. So I distributed a 5 through this group, and I had 15x for that term. Then I would have had minus 35, but I had a plus 3 here. Well, minus 35 plus 3 gives me the minus 32 down there. So now you can see I called this the fully factored fantastic final form of the answer whenever every term in there is multiplied and simplified as far as it can go. Up next. So on this page, I'm trying to go back and look at trig functions and make sure you don't get confused between when an angle is being squared inside of a trig function and then when the entire trig function is being squared. So here in the first one, I have the cosine of x squared. Only the angle is being squared. So I need to understand here the inside function is x squared. The outside function is the cosine of x. So I take the derivative of the outside first, and I can say, well, okay, the derivative of cosine is negative sine. I keep the angle, then I multiply by the derivative of the angle. Now I can say, well, that 2x times negative 1 is going to give me negative 2x sine of x squared. Final answer for that one. If I have cosine squared x, again, I can think of that as, well, it's the entire cosine function being squared. So the outer function is x squared, and now the inner function is the cosine of x. To take the derivative of that, I bring the 2 down in front, times the cosine of x to the first power, times the derivative of what's inside of it. Well, derivative of cosine is the negative sine of x. So now, the simplified answer for that, you just say, well, again, negative 2 times negative 1, that's where I'm getting the negative 2 cosine x sine x there. Now, I went ahead and threw in this other one. I said for fun, but it's actually trying to make sure if you really get the concept of the chain rule. I'm jumping from, on the last page, we had a 3-layer chain rule, to this one, I have an absolutely gorgeous 5-layer chain rule. Please notice, how do you count the layers? Well, I have the function x squared, that's layer 1, inside of the exponential function e to the x, that's layer 2, which is inside of this angle being squared, that's layer 3. That group squared is inside of the cosine function, that's layer 4, which then that cosine function is being squared, layer 5. So I can say, okay, 5 layers, deal with them one at a time. first layer, the outermost layer, the power rule. So I can say, well, since this cosine was being squared, again, I went ahead and treated it as the entire group to the second. That helped me see it. This 2 comes down in front of the group times everything left alone to the first power. Then you say times the derivative of what's on the inside of it. Well, the thing that's on the inside of it is a cosine function. So you say derivative of cosine is negative sine, keep the angle. Angles never change. Then you say, okay, yeah, but now that I've taken the derivative of cosine, I need to think about the derivative of that angle. But the angle is yet again a group to a power. So I had to say this 2 would come down in front of the group, 2 times e to the x squared. That's where that came from. Then you say, okay, now you have to take the derivative of what was inside of that group, but we know that the derivative of any exponential function is just that exponential function. So I said the derivative of e to the x squared is e to the x squared. But then you say, yes, but then you have to multiply by the derivative of what was inside of that exponential function. Derivative of x squared is 2x. Now please notice there should be 5 components of my derivative answer. Layer 1, layer 2, layer 3, layer 4, layer 5. Absolute gorgeousness. Now you can say, you can multiply all of these together. I have the 2x times 2 times a negative 1 times a 2. And I think I forgot my factor of x there in my answer, so I need to improve upon that answer here real quick. I'll say this needs to be a negative 8x times the group. So all of those multiplied together to give me negative 8x. And then times the e to the x squared. I had an e to the x squared times an e to the x squared. So I said, well, you have e to the x squared quantity squared. And then your cosine of the angle squared, and then your sine of the angle squared. Gorgeous answer there. Now I want to go back to one that uses the product rule again. So in this one we have the chain rule within the product rule. Factoring will be very important to make your answer useful. So in this one I had 3x minus 4 to the 5th power. So I said, well, the derivative of that, the 5 is going to come down in front, times the group to the 4th power, times the derivative of what was inside of that group. All of this times the second group, so I just brought it down. Then I said plus the first group, 3x minus 4 to the 5th, now times the derivative of the second. 6 had to come down in front, times the group to the 5th. My whiteout didn't want to be written over, so I had to drag my 5 down here. You can barely see it there. And then I said times the derivative of what was inside of that group. So that's where the 4x minus 3 came in handy. So now I come down here and I can say, okay, I need to simplify this. You need to look at everything we just did up there and pull out the greatest common factor. When I think of the greatest common factor, first of all, I'll think of the constant factors. The first term has constant factors of 5 and 3. The second one only has one constant factor of 6. So I can say, yeah, but 6 has a factor of 3 in it, so I can factor out a 3. Then I know I can factor out the group 3x minus 4 to the 4th power. They both at least have that. And I can factor out the group 2x squared minus 3x plus 5 to that 5th power. They both at least have that. When I factor out the greatest common factor, I can say what's left in the first term. Well, the first term you're going to have the factor of 5. That group and the 3 canceled out, but you'll have the trinomial left to the first power, plus the second term. 3 divides into 6, leaves you a factor of 2. You'll have 3x minus 4 to the first power times 4x minus 3 to the first power. Then what I've done from this step to the next is I already had this factored out, so I just rewrote all that part. But I needed to simplify this last factor that I had in the brackets. I knew it could be simplified much better than what it is currently. I distributed a 5 through the first group to get 10x squared minus 15x plus 25. In the second group, what I've done is I FOILed out the two binomials, and then I multiplied each term by 2. So I said 3x times 4x is 12x to the second times 2 is 24x to the second. Then I said 3x times negative 3 is minus 9x, but then I have a minus 16x right here between the negative 4 and the 4x. So that's minus 9x minus 16x, it'd be minus 25x. Minus 25x times 2 gives me minus 50x. The last term, negative 4 times negative 3, is a positive 12. 12 times 2, 24. So then again, I just brought down my first three terms. This last term in fully factored final form, you have to gather your like terms. You have 34x squared minus 65x, and then plus 25 plus 24 for plus 49. Fully factored final, fantastic form of the answer. The last one is me trying to show you a quick application with differential equations where we're supposed to be able to show that the original equation y is equal to any number a times e to the negative 2x plus any number b times e to the 3x satisfies the differential equation where I say I want the second derivative minus the first derivative minus 6 times the original function to be equal to 0. So I go through in here and I can say, well, I know that my first derivative here is just the derivative of e to the negative 2x, which derivative of any exponential function is that exponential function times the derivative of the exponent. That's where the negative 2 came from. Same thing in the second one. First derivative of b e to the 3x is just 3b e to the 3x. I would have had to multiply by 3. It's better to put it out in front. So the second derivative is also very straightforward. The derivative of the first term, you're just going to continually multiply that exponential function by negative 2 every time you take the derivative. So it became 4a e to the negative 2x. Same thing here. With the e to the 3x, you say derivative of any exponential function is that exponential function times the derivative of its exponent. So I multiply by yet another factor of 3 to get to 9b e to the 3x. Now notice, we were trying to establish that this equation is equal to 0. So I plugged in my second derivative right here, minus the first derivative right here, and then minus 6 times the original function. This must equal 0. Well, if you try to gather like terms, you would have a 4a e to the negative 2x plus 2a e to the negative 2x. That would give me 6a. But then I know that I'm subtracting that 6a e to the negative 2x right here. So in the end, the coefficient of e to the negative 2x is 0. They all cancel out. Same thing happens with the coefficient of e to the 3x. I would have 9b e to the 3x minus 3b e to the 3x. That would be 6b e to the 3x. But then notice we're subtracting 6b e to the 3x. Cancels out. You'd have 0 e to the 3x. We've just verified that yes, this differential equation, second derivative minus the first derivative minus 6 times the original function, would equal 0 where that equation is my original. Now hopefully this gets you a little bit more comfortable with the chain rule derivatives. Please keep in mind that you'll have several problems to work. Let me know if you have any trouble with them.